Welcome back, everybody. So I want you to think about how far we've come just in learning about likelihood. We've learned some other things as well, but just think about likelihood. So for likelihood, we've written down a model, a complete model of the universe in a sense, or at least the pieces of it we care about it. There is in that model a class of possibilities, and members of the class are indexed by the parameters that are going to give us estimation uncertainty because we don't know them, right, the alpha and beta. Once we know those parameters, then we can do all kinds of other things. How do we get to know those parameters? Well, we can't know them for sure, but we can estimate them. How do we do that? We take the model, we write down the likelihood function, we take the log of it and we get the log of the likelihood function. We then put it into code. In putting it into code basically means writing a function that represents the log likelihood function. We give that function to Optim, or some procedure to find the maximum. We get the maximum. We also get the variance covariance matrix of the maximum, which is the curvature at the maximum, which indicates how certain or uncertain we should be about those point estimates. From that, we now have estimates of which member of the class of models we've specified is supported by the data that we happen to have. And we also have uncertainty, so we understand how uncertain we should be about our conclusion. However, of course, our conclusion is not really in that space. Our conclusion is a transformation of those estimates into something that is a quantity of interest, or we would define as a quantity of interest, and it would be useful as a quantity of interest in conveying what we've done to a particular audience. So that's what we've done. But of course, so far, I've only given you the outline of how to do it. We've done it in a few very specific cases: the linear regression model, the stylized regression model for forecasting presidential elections, for variance function models. We're now going to start doing it for a whole range of other models. The first two models that I want to focus on are Logit and Probit models. They're for binary outcome variables. When the variable you're predicting, the dependent variable, is binary, just 0 or 1. When I teach you this, and as I teach you actually, as we talk about all of the other models that follow, every time I teach you a new model, we're going to use the same procedures that we have to specify the model and write down the likelihood function and turn it into code and calculate quantities of interest every single time. But as I introduce each of these models, I'm also going to give you some other things about it, some specialized things about it, because although I've given you an overall framework that helps us understand a vast array of models that are already out there and others that definitely are coming, we should also understand the particulars of any particular model, of any specific model, because they often come with specific things, with specialized procedures or different ways of interpretation. And so as I introduce Logit and Probit models today, we're also going to talk about quicker ways of understanding the functional forms and alternative interpretations just for binary variable models. These things will come up somewhat in the context of other models, but they're really specialized here. After that, I'm going to introduce general purpose rules for presenting and interpreting statistical results, which is the basis or the general format of how we're going to simulate results and produce quantities of interest. But first, let's do binary outcome variables. Let's get started. All right. So we have, for starters, I'm going to give you, as far as we can go, given the models we have already without introducing any innovation, and then we're going to slightly adjust it to get to binary, to get to models that are specifically designed for binary outcome models. So first, the linear probability model, which is a fancy name for running a regression on a dichotomous dependent variable. So it is possible to do that. Let's see what the consequences of that are. So here's the model. The stochastic component for a binary outcome, what would that be? Well, it's pretty clear what that is. It's a Bernoulli variable. Remember, we did that when we did probability. Bernoulli can only take on two values. The two values are mutually exclusive and exhaustive. Those are the only two values. You can't get both of them. There's nothing else can pop up. It is, of course, a model, but it's a reasonable and quite simple model. the probability of a 1 or a heads or Republican is pi. So pi here is a parameter. For starters, as we have it written down here, it's going to have a subscript I, so pi sub I. So there's a different probability of a 1 for each observation. Then we're going to have a systematic component added to that stochastic component, which for starters under the linear probability model is just going to be a linear function. So the probability that y is 1, given beta, which is the same thing as the expected value of y in this case, which is the same thing as pi of I, because that's the parameter of the Bernoulli, and it's the only parameter of the Bernoulli. And then the model itself is going to be pi of I is equal to x beta, which is equal to beta 0 plus beta 1 x1 plus beta 2 x2, etc. So that's the linear probability model. It's not a crazy model. It is used. Back in the 60s when it was very hard to run Logit and Probit models because we didn't have the computers to do it, people actually ran linear probability models. They're still run today in certain contexts. It's easier to correct measurement error in the context of linear probability models. There's certain types of corrections for endogeneity that people keep using linear probability models. So let's just get a feel for why we might want to generalize it. By the way, there's a third piece of this, which is yi and yj are independent for all I and j. It's the same assumption I've added before. It's just independence of observations. Okay, so the linear probability model. Here's a drawing of it. We have x on the horizontal axis, we have y on the vertical axis, and LPM for the linear probability model. It's just this line. I also have just presaging what's coming after the Logit and Probit models, so we'll show you those. We'll show you those after. So have a look at this. What's good and what's bad about this model? Why do we want to go beyond the linear probability model? What's wrong with this model as it is? Okay, so for some values of x, it could be that the linear probability model predicts a pi that's above 1 or below 0. In fact, you can see it in this picture. Because if x is over here and you go up to the linear probability model, well, then y is going to be above that dotted line, which is a 1. And if you make x small enough, then it's going to be below 0. So clearly that's not something that we would like. However, models are approximations, and maybe because of the simplicity of this model, it's okay for applications in which all the pi's are, away from 0 or 1, so that the reasonable predictions, even from a linear functional form, would be reasonable. Okay, but even if that's true, it's not going to get the uncertainties right. Okay, now ask yourself, why do we want the uncertainties right? Well, because that's what a scientific statement is. We always have to get the uncertainties right. That's really important. But it's also important to get the quantities of interest right. Right now, you might say, well, why didn't I just say that? Because I just explained that often, or sometimes, or for some applications, the pi's can be predicted accurately. But you need the uncertainties for some quantities of interest. Think back to the model we created for predicting presidential elections. So in one state, we had to predict the probability, it's a pi, right, that the Democrats win the election. So think about what that is. In that model, we were predicting the mean, so the mean distribution, but we were calculating the quantity of interest as the area to the right of 0.5. So that means that you could get the mean right, but if you got the distribution wrong, the area to the right of 0.5 might be completely wrong. If the variance is too big or the variance is too small, the area to the right of 0.5 might be completely off. So you have to get the whole model right for some quantities of interest. So that's another reason why we really do want to generalize the linear probability model when we can. Okay, so let's go to a straightforward generalization of the linear probability model, a very common model. In some fields, this is by far and away the most common model that's used not only for binary outcome variables, but since most of the outcome variables are discrete or binary, it's probably the most commonly used model in those fields. Public health probably, or some areas of public health, and certainly many areas throughout the social sciences. So this is the logistic regression model, or sometimes called the Logit model. Here's the model. So the stochastic component is the same as under the linear probability model. Its y is a Bernoulli, so it's a Bernoulli distribution. Same exact thing. The systematic component, however, takes pi and predicts it so that it is always between 0 and 1. And well, how does that work? How does it do that? Well, it takes x beta and it maps it, it squashes it into a Logit functional form. So we've looked at the Logit functional form earlier, but now we're actually going to use it. It looks like an escalator. Mathematically, this is exactly what it looks like, 1 over 1 plus e to the minus x beta, where x beta is just the same thing as in a linear regression model, beta 0 plus beta 1, x1 plus beta 2, x2, etc. We're also going to have this third assumption that was the same under the linear probability model and all the models we've shown you we've talked about thus far, which is yi and yj are independent. So it's basically the rows of your matrix are independent. Here are some Logit models just drawn out so you can have a feel for what they look like. The horizontal axis is x and the vertical axis here is pi, and no matter what x is, pi is always between 0 and 1. So think about this model, not only this model, but any time you see a model, you want to think about what's good and what's bad about this model. What's useful and what's not so useful about this model. Where might it be useful and where might it go wrong? Where might it mislead us? There's always a place where a model might mislead us because it's a model, it's not reality. So we have to find that, right? You have to push it until it breaks. Find its weakness. If its biggest weakness isn't so bad, then that's pretty good. Well, then we'll go with it. Okay, so ask yourself, you're seeing a model, you should always ask yourself, what's good, what's bad? Okay, so the probability of y is always between 0 and 1 for any y, so it looks like an improvement over the linear probability model. I've shown you the Logit model. We can make one little change for a Probit model, which is instead of using 1 over 1 plus e to the minus x beta for the systematic component, we can use this big phi, which is a cumulative normal distribution. Actually, it's just not used for the normal, it's used for its functional form of x beta. So what's good and what's bad? Well, it could be more flexible. This escalator curve as a Logit or even as a Probit is symmetric. There's nothing saying that it really should be symmetric. I mean, it might be that there's a long, slow increase and then it just sort of curves off at the top, right? Or maybe it curves up at the bottom and then it goes like this, and right. So there's nothing that says it actually has to be a Logit model if it's not a linear probability model. But this is a reasonable starting point. Certainly, it looks like it's an improvement over the linear probability model. Okay, so let's write down the Logit model's log likelihood function. Okay, so first, just like we did for all the previous models, we're going to write down the probability density of all the data. How do we do that? Well, we write down the Bernoulli distribution, and then so that's the first assumption of the model, the stochastic component. Then we take the third assumption of the model, which is the independence assumption, and multiply all those Bernoullis, one for each observation, by taking this product sign and putting it in front of the Bernoulli. And then we have the second assumption of the model, which is the logistic functional form, and that's what pi is. And then we just have to substitute the right-hand side of that equation over there on the right for the left-hand side in the probability density of all the data over on the left. So the log likelihood then is equal to the probability density where we take the log after the pi is substituted in. Now, notice here, I skipped writing down the likelihood with k of y in there. And why did I do that? Well, I perhaps could have, maybe even should have done it just to remind you, although I'm reminding you verbally, so give me a break. In any event, every time we're going to have k of y in there, every time the likelihood is going to be proportional to leaving out k of y. And so we're always going to know it's there, so we don't actually have to write it down every time, as long as we know what we're doing. The log likelihood then would always have a term in it, which is the log of k of y, but it would always turn red and disappear because it's not a function of the parameters. It's never a function of the parameters. So it always goes away. So there's no reason to first write it. I mean, so we're not required to always write it down and then always drop it out. right? We just have to understand that we're following the likelihood theory of inference, and in the likelihood theory of inference, that is what happens. So we have a representation of the log likelihood function, which is the log of this equation, right? It's the log of this, so it's y log of pi, 1 minus y log of 1 minus pi, and that's exactly what we have down here. Once we substitute in the pi with the Logit functional form, we get this, this expression. And then it turns out you can rearrange this a little bit and get that. So you can convince yourselves that the second line is equal to the third line. I promise it is. It's just a little algebra. It makes it a little simpler. You don't need to do it, right? You could program. We're going to have to program this up, of course, after we have the mathematical form here. I would rather program up the last line than the second to last line, but you certainly could program up the second to last line. There's nothing wrong with it. But the more elegant your math, the less likely it is there's going to be a mistake. So it's a good idea to do that. So what do we do with this log likelihood? Well, I've already told you we're going to write down this in code, but let's just think conceptually, what does this give us, right? This gives us a function into which we can guess values of beta or query this function with chosen values of beta that we put into the function, and we ask the function how likely is any particular value of beta, any particular values of the vector beta. And we could choose 1, 1, 1, 2, and then we could choose 1, 1, 1, 2.6, and then we could choose 0, 2, minus 7, 8, and we can put each of those in, and the log likelihood would come out of the other side. And that's basically what it would give you. Okay. With that, we can find the maximum, and we can do other things. So we put this in code. We give the code to Optum, which is the procedure in R. It will then put in values for the vector beta itself, and it will keep doing that, lots of values, until it finds the one value of the vectors of the beta vector that gives the largest value of the log likelihood, and those values of the parameters are known as the maximum likelihood estimates. Okay, so how do you interpret the beta hats that come out of this? Well, they're the maximum likelihood estimates, but still, how do you interpret it, right? Remember, this is the functional form up on the right here, right? So how do we interpret the beta from this expression? Well, I don't know. I mean, how would you interpret it? We're gonna have to think about that. Okay, so let us get there. Okay. All right. So interpreting functional forms. I'm going to do it in a number of intuitive ways to give you a feel for it. I'm going to give you a rule of thumb so you can get a very quick sense. And then when we're all done, I'll give you a much more elegant way by simulation. Okay. So here's some functional forms. These are not Logit models. These are more general functional forms, just to give you a feel for the kinds of ways that we could represent our results. And horizontally we have X, and vertically we have Y in this case, with uncertainty represented. So this is one way of presenting our results and to interpret functional forms quite generally. When you have functional forms and you're interpreting them, you don't use the observed values of X, you use the theoretical range of X, that you could put in different values into the functional form and see what comes out the other side. Because you're specifying a whole functional form, you can explore it as you choose. If you have more than one X, then you can't always do it in a two-dimensional plot. You might need a surface plot with X1 this way, X2 this way, and the height being Y. You could also, in a two-dimensional plot, have X horizontally, Y vertically, and have two lines, one for X2 equal 1 and X2 equal 2. And so there's lots of creative ways of doing this, but you need to focus on those things. You can also look at marginal effects. That is, you hold some variables constant at their means, and or some typical value or the most common value in the data or something like that, and move one of the variables, one of the X's, and see what happens to Y. We can look at average effects, which is computing the effects, perhaps a causal effect for every observation. We see what happens if you change one of the X's for each observation, and then we can average those. So each of these gives you an option for how you might represent your results to your readers. And the choice here of what the right way to do that is, it's your choice. You get to make the decision. But the choice of whether, or the decision about whether it was really right, that's your readers. And you don't exactly know who your readers are because they're this big amorphous group of people who are known as anonymous reviewers and anonymous readers. And you're going to have to figure out who they are, what they're thinking, what they would be interested in, what would get their attention, and what would be compelling to them. And so these choices are always with respect to that, not with respect to me. Now, don't try to convince me. Try to convince everybody. I'm one of those everybody's, but try to convince everybody. That's how you have to think about this. There isn't a correct way to do it. That's why I'm giving you more than one answer. Okay. All right. So one way to interpret functional forms is fitted values. So we can think of fitted values. You already know how to calculate predicted values in regression. We can do this in Logit too, and it turns out we can do it in any for any functional form. We can calculate fitted values given specific values of x as follows. What you do is you choose a value of x sub c, that's c for choice. In one way, we could choose typical people or typical countries or stereotypes or things like that. So you take the xc and you stick it into the functional form. One way of doing this, with the maximum likelihood estimate, out will come an estimate of theta hat. And so here's an example for men age 20 who live in Chicago and whose income is $33,000. We could calculate perhaps the probability of voting in a Logit model is 0.2. And a female who's 27 in New York City with an income of $43,000, maybe the probability of voting is 0.28, and etc. So this is one way of representing the results so that I think anybody could understand, even somebody who has no idea what a Logit model is and has never done any statistical analysis before. And that's actually who you need to pitch to. Not only who you need to pitch to, because you also need to convince the people that understand the models you're running, but you need to be able to convince people that just are interested in the substance, because that's why we're here. That's why we're doing quantitative analysis. It's for the substance. It's not for the quantitative analysis. So you need to be, you must, it is important that you do focus on those people, right? Focus on the people interested in the substance so that we can focus on the substance. That's sort of how we do it. So a list of fitted values for typical people or observations in your sample is one way of exploring the possible results. It's a reasonable way, and it may be useful for certain audiences who you think you might have. We always include a measure of uncertainty, a standard error, or confidence interval for everything, except actually for a probability, because a probability is this odd quantity of interest where it's a point estimate, yes, but it has uncertainty embedded in it, right? It is already a probability. So yes, you could have the probability of voting in that first line as 0.2 plus or minus 0.05, but that's just level after level after level, and you have to stop somewhere. And for probability, I think it's reasonable to just stop at your best estimate is that probability, and that's okay. For anything else, you certainly want to have two numbers, and they should be separated. So it's also important that it be easy to communicate, and the definition of easy to communicate depends entirely on who you're talking to. All right. It is difficult, of course, with a list of these typical cases to be comprehensive, even though it is easy to communicate, right? So these can communicate very well to anybody, pretty much, but it's hard to represent the whole full complexity of your results with this table. So you might do it for certain things, but I don't think I would do it all the time. And the other thing is, it's better by simulation. All of these things are going to be better by simulation. I'm giving it to you this way, and in particular, this way here, right? Because this is going to give you a quick estimate for how to calculate it. You just stick in the maximum likelihood estimates, and you get out a predicted value that you can use here, right? So it's possible to do that. It is better, almost always, to do it by simulation. But this gives you a feel because it's simpler and it's straightforward. Okay. All right. So another quantity of interest from logit models and from other types of models are first differences. They're a great way to interpret functional forms in a way that's parallel to, analogous to, and really very similar to, and could be used for causal inferences. Okay. They were also called risk differences in epidemiology. And so here's how it works. You define a starting point and an end point for each of the explanatory variables. So often what you do is you take many of the explanatory variables, all but one of the explanatory variables, and set them at, let's say, their means, the starting point and the end point. And then you move just one of them, just one of the variables, and you see what happens if you move one of the variables, hold everything else constant, and see what the effect is. You could, of course, have the starting point be everyone in New York, and the ending point, or the average in New York, and the ending point being the average in Chicago, and you could see what the effect is of that. There's a lot of ways of doing it, but this gives you the freedom to make those kinds of decisions. Okay, so that's the starting point and the ending point. And then we calculate a first difference. So a first difference is the difference in the outcome of the functional form for the ending point. That's g of x sub e for ending point, given beta hat, minus g of x sub s for the starting point, also given beta hat. And that difference is your first difference. So for the linear model, it's just the difference between those two y hats, basically. For a logistic model, it's the difference between the two pi's, and you can plug in that functional form. And so here's an example. If we imagine swapping a man for a woman and keeping everything else the same on average, then maybe the probability of voting changes by 0.05. Or if we swap a person who's 65 with somebody who's 75 and you leave everything else the same, maybe the probability of voting drops by 10%. Or if you move somebody who has all the same characteristics but move them from New York City to Madison, Wisconsin, maybe the probability of voting increases by 0.26 because everybody in Madison, Wisconsin tends to vote, etc. So this is another way of representing results. It may be of more interest when you're interested in what happens as things change. We will get into much more detail on precisely what is a causal effect and when you can use analyses like this in order to claim that you have estimated or a causal effect and therefore made a valid causal inference. Okay. Again, this is going to be easier by simulation. You're going to get point estimates and uncertainty estimates, etc. But this is an intuitive way of getting a feel for what it means. Okay, so here's another way of interpreting functional forms that's even easier, and it's using derivatives. So here's a functional form. This is a logit curve. On the explanatory variable, on the horizontal axis we have x, on the vertical axis we have the probability of 1. Probability of voting, let's say. This is great for very quick interpretation. It's probably not great for presenting results because you can usually do better, but you're going, since if you're going through these slides and you're listening to these lectures and perhaps you're taking this class, you are officially a methodologist. You are going to be thought of as a methodologist. Wherever you are in the future, you're going to have an office somewhere probably, and everybody else on that hallway or walking down that hallway is going to think, I have a methodological question, I'm going to go talk to you. Okay, so you get that, right? People are going to think you're the methodologist, and when you're the methodologist, they're going to come into your office and they're going to say, here's a set of results. Tell me what they mean. Now, the right answer is to say, don't just give me the printout of your logit coefficients. Those are not very interesting, right? They're not in the format that could convince me of anything, or even it's not even particularly interesting or easy to interpret at all by themselves. So why don't you go and simulate and calculate something that is really of interest? The problem is you can't tell people that because they're not going to go do it. And you're not doing your job of being very helpful to them. So how can you be helpful to them? Well, you want to get them to do that. Absolutely, definitely, that's what you want to get them to do. But still, you want to be useful right then and there. How do you do that? Well, you want to be able to interpret those numbers. How are we going to interpret those numbers? We can use the derivative rule. Here's the derivative rule. You take the derivative of theta. Remember, theta is the thing in the generalized functional form with respect to one of the x's. That is, how much does theta change if you move one of the x's just a little bit? The derivative rule is a linear approximation to whatever functional form the person chose. So that's basically what we're doing. Whatever functional form the person chose, we're going to take the quick linear approximation to it. Okay. So if the function that they chose is linear, then the derivative of mu, that's what theta is in this case, the mean, the expected value, with respect to x sub j is beta sub j, right? Because it's a linear functional form. You just read off the coefficient. In the Logit model, the derivative of pi, and pi is the thing that's equal to g of x and beta. The derivative of pi with respect to xj is the derivative of the Logit functional form, 1 over 1 plus e to the minus xj with respect to xj. And that thing, if you actually write it, if you actually do the calculus, the answer is beta hat sub j times pi hat times 1 minus pi hat. So it just actually is equal to that. So you can actually calculate that. Okay, how does that help us interpret the coefficients that just got slid on your desk in front of your nose and you have to provide some useful information to them? Well, the effect, the linear effect of x on y is going to be different for different values. So let's think of a linear approximation to this curve. A linear approximation to this curve down here is going to be relatively flat. Over here it's going to be pretty steep. Over here it's going to get less steep, and here's an example right here, I've drawn on here, beta pi 1 minus pi, right? Just like that. And as you get up here, it gets flatter again, all right? So, I don't really want to have to tell the person, look, for every coefficient, there's really a lot of effects depending upon where you are. It becomes a big mess. So here's one quick way of doing it. Let's just pick the largest possible value. It's like, where's the largest possible value? Well, clearly, the largest possible value is in the middle, okay? Right, because that's where it's the steepest. Where is it the steepest? Well, it turns out it's the steepest when pi is 0.5, okay? So that, in fact, pi times 1 minus pi is maximized when pi is 0.5, right? Because any other number, pi times 1 minus pi, will be smaller than if pi is 0.5. So let's just take the largest possible interpretation, the largest possible value. So the largest possible value is beta hat divided by 4. So what do? They hand you the coefficients, and they say, what the heck are these? And before you tell them the right way to do it, you look at them, you divide them by 4 in your head. Not that hard, right? You divide them by 4 in your head, and you interpret them like linear regression coefficients. That's not the correct way to do it, but it's an approximation. When would it be wrong? Okay, I'm going to try to explain that we always ask that question. When would it be wrong? It's going to be wrong if most of the data have a very high probability or a very low probability of actually happening. Then you're going to be up over here. Most of the data is going to be down here, and this maximum value is not going to be realistic. But that's okay. This is an approximation. It's a quick interpretation. It gives you a sense of what's going on so that you could then give the person suggestions in addition to just do it the right way and do simulation. So you can get a sense of, extract some value and knowledge from what the person actually did run. Okay. Suppose the person ran a Probit rather than a Logit. What do you do? So I did the calculation, and it turns out the maximum value for a Probit, of course, looks very much like a Logit. It's very similar. I've never seen an example in the social sciences in which you have enough data to be able to distinguish a Logit curve from a Probit curve. And so, when do you choose one versus the other? It depends what computer program is more handy. I tend to like Logit rather than Probit because the functional form you can write out, and that's what it is. And the functional form for Probit is this phi thing, and it's numerical, and you can't write it out. But it really doesn't matter which one you use. If the coefficients that they slide onto your desk are Probit coefficients, instead of dividing by 4, you multiply by 0.4, and you get a number, and you interpret that number as if the person had run a linear regression. It's approximate. It has the same disadvantages as using this rule of thumb for the Logit, but it's a great way of doing things. I've never actually seen this in a textbook, but I'm not sure I've seen it anywhere. But just take it, use it, and remember it. It is quite useful. So each of these are approximations presented so it's easy to remember. So remember, okay? Deal? Okay. All right, so let me give you now some alternative interpretations of binary models that are not so common for other type of outcome variables. All the other things I've shown you before apply to other outcome variables. And the general rules for presenting and interpreting statistical results based on statistical simulation will apply for all types of models. But these alternative interpretations of binary models are mostly are designed for binary models. There's some other models that it'll be relevant for. As I said earlier, for every model, there will be something special, something unusual, something that is tuned to the peculiarities or special issues with respect to the type of data or the type of model that we're using. So alternative interpretations of binary models. So from biology, where the zeros and ones are dead and live bugs. So imagine you have bug spray, you got a whole bunch of bugs, you spray the bug spray on the bugs, and how do you know how successful it was? Because usually all the bugs don't die. So you just count them up, right? You just count up how many bugs died, right? And the only thing you get to see is dead or alive bugs. Okay, so let's think about this. What we could imagine is that there's a measure of the health of bugs, or health, or the propensity to vote, right? There's some underlying continuous variable which you don't get to see, it's unobserved, but that's the thing that we might actually care about if we could see it. So let's imagine that. There's a Y star. And then we can build a model for the Y star and then figure out how to get the observed 0, 1 in there afterwards. So for starters, there's an unobserved variable Y star. Y star has a distribution, which we'll specify later. Right now, I'll just call it P. So P of little Y star given mu. Mu has a functional form. Let's just make it linear. So mu is equal to x beta. And now I have a very quick way to write the third assumption of the previous models. Yi is independent. That's the two lines. This is the perpendicular lines is another way of writing independence. So y of I is independent of y of j given the x's. So I've basically written down all three components of this statistical model just in a more compact format. So one quick way of making sure you understand what we're asking is what model that you know has y star observed and p normal. So if you have y star observed and p normal, what model is that? Bing, that's right, it's a linear regression model, linear normal regression model. Okay, but in this model, I have y star that's not observed. So, and I haven't told you what p is yet. So it's not observed, so our outcome variable isn't even observed. So we have to observe something as an outcome variable, otherwise what are we doing? So we're gonna have an observation mechanism. Not an observation, but an observation mechanism. The observation mechanism is that y star is unobserved. There's a realization of y star that comes when you draw it from its distribution. When it is drawn from its distribution, when it is produced from the data generation process, you then get, not y star unfortunately, but you get a 0 or a 1 depending upon whether that bug is alive or dead, or depending upon whether the person votes or doesn't vote. Okay. And so that's basically the idea. And so we imagine that y star, this y star, is this continuous unobserved underlying variable. And if that variable is less than or equal to some threshold, sometimes called tau, but for now we're just going to imagine it's a 0. If it's less than or equal to 0, then we observe a 1. If it's greater than 0, we observe a 0. So we only get to see the binary outcome variable, but we're imagining that it comes from a more interesting underlying continuous variable. If only y is observed and y star is a different distribution that you haven't heard of before called the standardized logistic distribution, and this is the standardized logistic distribution. It's a distribution. It looks a little like the normal. It looks a lot like the normal distribution. It has one parameter, mu. It's a new distribution. I just dropped it in here. But if y is observed and the p up here follows this particular distribution, then it turns out you get the Logit model. Well, why? Okay, I can prove it to you. Okay, so the proof, remember, I'm not going to usually do the proofs unless they're useful, unless we get some intuition from them. So I think if you're like me, when I tell you this, that if y is observed and this thing is a standardized logistic, you get the Logit model. I think the reaction you probably have is, okay, but like why or how or what, okay? So I can show you in one line, it's going to be straightforward, okay? So the probability that y is 1, right? The probability that we see or we are given a bug that is alive, right? Or the person who actually votes, that probability is going to be the same thing as the probability of the underlying unobserved continuous variable being less than the thresholds, because we've said that when it's less than the threshold up here, then that's when we would observe a 1. So this is true by definition, right? We see this as a 1 when this is less than 0. Okay. So what's next? Well, what is the probability that y star is less than 0? Well, that's the probability that the standardized logistic distribution is less than 0, or it is the integral of the standardized logistic distribution from -infinity up to 0. Okay, so it's, by definition, this thing is absolutely true. It's the cumulative standardized logistic distribution, right? That's that notation. It's often F is the cumulative distribution. Now, what is the mathematical form for this? If we did this calculus, right? We take this distribution and then we take the integral, right? And we figure out the calculus and we figure out, well, what is the form of the standardized logistic distribution, which Gary pulled out of the air, right? That's the standardized logistic distribution. What is the cumulative distribution of it? Hey, it's the Logit functional form. Isn't that cool? Okay, now, I'm sure that whoever came up with this originally, they had this. They were using this. It was useful on the last page. It was useful all previously in these notes. We don't need to have this whole story about the standardized logistic distribution and unobserved continuous variables. So I have no doubt that this was born in the universe before this, at least in the context of Logit models. But that's okay. We can maintain this theoretical model of the universe where there's this unobserved variable. If it follows a standardized logistic distribution, then the probability of that y is 1, that is this pi for the Bernoulli, right, turns out to be exactly equal to the Logit. So assuming this functional form, or not assuming the functional form, but assuming that there's an underlying continuous variable that follows a standardized logistic distribution, are the same thing. You can think about the same model in 2 different ways and you'll get the same answer. That's convenient because then you can pick one depending upon what you feel comfortable with and what you feel comfortable conveying to an audience with and what you think your audience would feel comfortable with. Okay? And what fits better to the substance. Now, of course, it doesn't matter in the end because they're the same, but still pick a way that your audience would understand. Okay, so this is the Logit functional form. Okay, you can get a feel for this. I drew this as tau rather than 0, but remember I said these could be tau. So this is the cumulative part. This is the probability that y star is greater than or equal to 0 or tau, just to give you a feel for it. Okay, I'm going to make this one more step, or maybe even a couple more steps more complicated, which is sort of interesting. This is going to have the same setup for Logit, but with one change. So the stochastic component, instead of saying that this P is a standardized logistic, instead it's going to be a stylized normal. Okay? So under the Probit model, also from biology, if we just make this a stylized normal instead of the standardized logistic, what happens? I mean, I think you know what's going to happen. It's going to be a Probit, right? So let's get there. Okay, so the systematic component, probability that y is 1, is equal to the cumulative distribution. We know it's the cumulative distribution of this normal because of each of the previous steps that we just did on the previous page, right? So this is 1 when y star is less than 0. Y star being less than 0 is the same thing as the integral of this normal distribution from -infinity up to 0. That's exactly what this is. Then this thing, the integral from -infinity up to 0 is equivalent to the cumulative distribution up to x beta. And this is actually exactly the form of a Probit model, which is cool. So we have another interpretation that parallels the previous one. All you do is you swap out the distribution of P, of the unobserved variable, for stylized logistic. Now, should you choose Logit or Probit? Here's one way of thinking about the difference. Okay, so you have to think about an unobserved variable. So are you good with assuming your unobserved continuous variable that you only observe the dichotomous realization from is normal or style or standardized logistic? Which one? Because if you know which one, then you will automatically get either Probit or Logit. Now, I really don't think that you're going to have an answer to that question. You might, if you spend a lot of time doing theory, you might have some theoretical reason to choose one versus the other, and that's cool. But now you can at least have a feel for what the differences are. Okay, so if it's normal, then you have another way of interpreting the results, which is sort of interesting. So how do you interpret Y star? Well, one unit increase in Y star under this model is one standard deviation unit, right? Because the standard deviation of Y star is 1, right? So if anything that increases Y star by 1 is increasing Y star by 1 standard deviation unit. So we can interpret beta directly here. You don't have to divide by 0.4 or anything. You can just say that beta are the regression coefficients when you run a regression of Y star on X, right? A linear regression coefficients of Y star on X. That's the cool thing. But with the dependent variable being Y star. So it's sort of pretty cool that you can estimate the effect of X on an unobserved variable because we have the observed binary realization of it, okay? And you can actually interpret it. You can interpret beta hat J, like let's the coefficient on the jth variable, let's say, is as what happens to Y star on average when xj goes up by 1 unit holding constant the other variables. So, for example, if x sub j, if education goes up by 1 year, maybe the propensity to vote increases by 1.2 standard deviation units. So you can actually say that. Now, of course, you are saying that the propensity to vote, an unobserved variable, has increased by 1.2 standard deviation units in an unobserved variable, and so it's a little disconnected from reality, but or it's got a few extra layers of theory in there. Okay, I'm going to go one more layer of theory, and to do that, we're going to go to economics. Okay, so here's a Logit and Probit interpretation for how economics likes to, or at least liked to, or at least introduce these models, or in fact, how they first got there. So here's some definitions and the way they think about the world. So there's a utility for one of the choices. I'm going to call this the Democratic candidate. We'll call that U to D, to sup D. This is the utility. Utility is how much goodness you get out of that choice. And then there's also a utility that you would get for choosing the Republican candidate. There's different utilities may be different for each observation, so there's sub I. There's a utility difference, and the utility difference is the difference in voting for the Democrat minus the difference in voting for the Republican on the scale of utility, whatever that scale is. We don't see the U's, and we don't see the Y star, right? So in the previous example, Y star was unobserved, and now we have the U's that give rise to the Y star. So that's why I mean it's one level more complex. We're still going to have an observation mechanism. We're not going to see the U's. We're not going to see the utilities. We're not going to see the difference in the utilities, which is the Y star. We are going to, however, see the realization, which is a 0 or a 1. So if the person votes Democratic, we're going to assume that the person had more utility from voting Democratic than voting Republican. And that implies that there was a utility for voting Democratic and a utility for voting Republican, and one was larger than the other. So let's make some assumptions. First of all, we have the independence of the utilities. You have a utility from the Democratic candidate and a utility from the Republican candidate separately. That may or may not be true, but we're going to assume it. Each one of which follows a distribution. We'll specify a distribution later on. And in fact, later on is now. So if this P is normal, turns out you get the Probit model. And if the P is a new distribution that we're pulling out of the hat, a new distribution, you haven't heard of it before, if P is the generalized extreme value distribution, then you get the Logit model. And that's sort of cool. Well, let me actually go back for a second. Okay, so why is this? So how is this that if P for utilities, remember we're now going to make assumptions not on the distribution of y, but on the distribution of the u's. So if you have a distribution of the u's, each of these is normal and they're independent, then this is normal, and they're independent. That implies that y star is normal, because the linear combination of independent normal variables is normal. So I didn't make any assumption about y star. I derived it from the economist's first principles, which each of these you have to be comfortable with the assumption that they're normal. But if you are, then the difference of them is normal if they're independent. And therefore, since if this is normal, we get a Probit model, we're getting a Probit model. Okay, so what about under the Logit model? So if we make this a generalized extreme value distribution, now where the heck did that come from? Oh, hang on a second. Okay, so if the u's follow a generalized extreme value distribution, it turns out there is another theorem that says the difference in independent generalized extreme value variables follows a standardized logistic distribution. Okay, so if this one is generalized extreme value, this one's generalized extreme value, and they're independent, then that difference y star is standardized logistic. And we already know from the previous slide that when we did the Logit model, that y star then is standardized logistic, and if it is standardized logistic, that yields the Logit model. Okay, so now think we have three justifications for the same binary model. We could just assume the binary functional form. We can go one level up and assume there's an underlying unobserved variable that gives rise to the Logit functional form once we assume a distribution about them. We could go two levels up and we can say that that the utilities have distributions, and the differences of the utilities of those distributions produce another distribution, and that therefore results in the Logit model or the Probit model if you go the other way. Which of those do you prefer? There isn't a correct answer here. It depends upon what you're accustomed to, who you're writing for, what is most convenient, and what fits best with your theoretical what fits best with the particular problem you're analyzing. I tend to like to stick to the data, and levels upon levels of theoretical assumptions that have no extra usefulness, I tend not to focus on. So if I had to pick, I would usually pick just the first one that I presented without this extra interpretation from biology and the extra interpretation from economics. But I can certainly see that there are some audiences and some substantive problems for which I would want to use this kind of interpretation. So what's important to you depends upon what you're analyzing, what field you're in, who you're writing for, etc. And it may be that you prefer one, but you need another in order to convince people. So just keep this in your toolkit. It is also the case that you just may see this described somewhere. And if it's described somewhere, you'd better understand what it is. So now maybe you do. Okay. So you should also think, when would you choose the linear probability model or Logit or Probit? Because at the end of the day, those are the models that we're actually running. Okay. All right. So let's stop there, and then we'll continue next time on general rules for presenting and interpreting statistical results. And that's going to be the cool thing, because we will have a general set of rules that will apply regardless of what the statistical model is. Okay, see you next time.